Okay guys, welcome back. In this video we will talk about the deflection of beams, but with the different method than the one we discussed in the previous video, which was double integration method. This method is known as the moment area method, right? And as evident from by its name that the bending moment diagram will be involved in this method, unlike the previous one where we had to find the derive the bending moment equation and just double integrate it to solve, right? So the moment area method is a semi-graphical technique for finding the slope and displacement at specific points on the elastic curve of a beam. Application of a method requires calculating area segments of the beam's moment diagram, right? So you have to draw the bending moment diagram and then you have to find the area of the bending moment diagram. There are basically two theorems involved in this method. Theorem 1, which is about calculation of the slope, and theorem 2, which is about deflection of the deflection or displacement, right? So theorem 1 simply says that consider this beam, a simply supported beam, right, which is subjected to a certain kind of loading. It can be UDL, it can be UVL, or a combination of both, and the beam will deflect in this shape as presented by this elastic curve. Now consider 2 points A and B on this beam, right, and draw the tangents on these two points. This is tangent at A and this is tangent at B, and these two tangents are making an angle theta at B with respect to A, right? So this is basically the slope of point B with respect to the tangent which is drawn from point A, right? And see, it is in the counterclockwise direction. Now when you understand this, let's consider a simple area element of thickness dx on this beam, right? And this dx is shown here, and when it is subjected to moment, as you can see, so it will deform like this, right? The length of this central line or the neutral axis will remain same, and it will be dx just like before the deformation it was, right? And when you draw the tangents at both the ends of this neutral axis, so you can see the both the tangents are making an angle d theta, right? So what is happening here is that by considering the equation 10 of previous lecture, which was the double integration method, right? And this was the equation where ei d square mu by dx square was equal to m, and when you just write this equation in this form, right, so you can see that this is the slope, the rate of change of mu with respect to x is basically the slope. Since the slope is small, then theta is equal to d mu by dx, and therefore you can replace this value by theta. So this will become d theta, right, and the dx will be multiplied on the other side, and ei will be divided on the other side. So m over ei into dx is our new equation, and this equation comes from the previous equation which we proved in the method of double integration. So this is our equation 11, right? Now if the moment diagram for the beam is constructed and divided by the flexural rigidity, see, if you construct a bending moment diagram, you got the values of m, right, and you divide the values by ei, so you will get a bending moment diagram where the values will be in terms of m over ei, which can be seen here. So this is your x-axis, and this is which shows the length of the beam, and this is your y-axis which shows the values of m over ei, right? So this is the bending moment diagram, but the value of bending moment is in terms of m over ei. So if you can see the same area element that we considered, right? So the dx is the width or the thickness of this element, and the height of this element will be m over ei. So it is a rectangle, and the area of rectangle is simply the length into height, right, the multiplication of two sides. So therefore this equation indicates that d theta is equal to the area under the m over ei diagram. So we have highlighted this area to make it prominent that the area under this curve of bending moment, this area, this is basically equals to this d theta, which is the slope or the rotation of this small element, right? So it is for this small element or segment dx. Now what about this whole segment between a and b? So you just integrate this dx segment from a to b, and you will find the whole area under the curve from a to b, and it will be equal to this theta b by a, right? So integrating from a selected point a on the elastic curve to another selected point b, we have theta b by a is equal to integration from a to b, the same value m over ei into dx. See this m over ei into dx, and when you integrate this d theta, it becomes theta. So this result forms the basis for the first moment area theorem, which says that the angle or the rotation which is measured in radians is equal to what? Between the tangents at any 2 points. In this case the points are a and b. So between these 2 points the rotation or the angle is equal to the area under the m over ei diagram between these 2 points, right? So simply just measure the area under the bending moment diagram between these 2 points, and that area will be equal to the rotation or the angle or the slope, right, of the beam between these 2 points. So the notation theta b by a refers to the angle of the tangent at b measured with respect to the tangent at a. Please note that the angle is not measured with respect to horizontal, but it is measured with respect to the tangent drawn at another point, right? From the proof, it should be evident that this angle is measured counterclockwise. As I mentioned earlier, that the angle is in clockwise direction and it is taken as positive. If it is in counterclockwise, right? If it is clockwise, then it will be taken as negative. See, conversely, if the area is negative or lies below the x-axis, the angle theta b by a is measured clockwise from tangent a to tangent b. So it's always counterclockwise for the values to be positive, and it's clockwise for the values to be negative. So first theorem was about the slope or the rotation or the angle, and the second theorem is about the deflection or the displacement, the vertical displacement, right? Now let me take you to the same beam. This is the same beam as we discussed in the previous theorem, theorem number 1. The simply supported beam subjected to certain kind of loading. 2 points A and B are selected, and small element of thickness dx is also selected. Now let me just make it more visible. This is the same figure, right? The figure 2a, and 2a is plotted here. Now this is the deflected shape of the beam, right? You can see that. Now at point A we have drawn a tangent which is called tangent at A, right? And at point B we have drawn another tangent which is called tangent at B, and the distance of this point A from the tangent B, this vertical distance, this is called TA by B, right? And we are interested in calculating this distance. Now in order to calculate this distance, just assume or consider this small element dx that it is deformed just like previous example, just like this one. Okay, it is subjected to m and it will deform in this way. So we can draw two tangents from its two ends, right? And it forms d theta. The angle between the tangents is d theta. So similarly, when you draw one tangent at this end of the dx, it is like this, and the other tangent when you draw at the far end, it will be like this, and the angle between these two tangents will be d theta, and this length of the arc, this will be equal to ds prime, and its vertical component will be dt. Now let's see that Using the circular arc formula, we note that S is equal to theta into R. So in our case, this R is X, right? The X is the distance from the center to the end of the arc. So X is our R in this case, and S is dt, as I explained here, right? So this is the vertical component is this dt. So we can write the equation of S is equal to theta R in terms of S is dt. So dt is equal to X into d theta, right? So this is our equation of this small element. Now substituting equation 11 into this equation and integrating from a to b. Now as we derived equation 11, where d theta was equal to m over ei into dx, therefore we can see that dt is equal to x into d theta. So we can put the value of d theta here. So d theta is equal to m over ei into dx. So dt will be equal to x into m over ei dx, right? So we substituted and we just integrated from a to b. So dt will be converted to t a by b will be equal to integration from a to b, and the same value x, and in terms instead of d theta we will put its value, which is m over ei into dx, and this is our equation 13. Now since the centroid of an area is found from this equation, x bar integral dA is equal to integral of x dA, and integral of m over ei dx represents the area under the m over ei diagram. So we can also write the previous equation 13 in this form, which is te by b is equal to x bar integral from a to b m over ei dx. So this is our equation 14, and here x bar is the distance from a to the centroid of the area. This is, for example, the area between a and b, and this is the centroid, and the centroid is somewhere at a distance of x bar from a and x bar prime from b, right? So the distance may not be the same between a and b. So from here we can state the second moment area theorem, which says that the vertical distance between the tangent at a point A on the elastic curve and the tangent extended from another point B, right? This is tangent A and the point A, and this is the vertical distance with tangent B, right? It equals the moment of the area under the m over ei diagram. So previously when we were talking about the slope, it was equal to the area under the MEA diagram, but here it is equals, the deflection is equal to the moment of the area under the m over ei diagram between these 2 points, right? And this moment is calculated about the point A, where the vertical distance is to be determined, since ta by b is the vertical distance about point A and it's not about point B. So keep in mind while calculating the deflection in this case. Note that ta by b is not equal to tb by a, as I mentioned that the distance may or may not be the same. So if it is equal, then no problem, but if it is different, then there will be a problem, and you need to calculate it for both of them separately. Now considering the example 1, which is a simple example, it says that determine the slope of the beam shown in figure 3a at point B. This is a simple cantilever beam subjected to a point load, and at its free end it is saying that just calculate the slope, right? So slope is our theorem number 1, if you remember, and just drawing its bending moment diagram as seen in figure B, and converting that diagram into m over ei. In cantilever beam you can see that the bending moment is equal to p into L, and just dividing this PL divided by EI will give you the PL over EI bending moment diagram, right? M over EI, and drawing its elastic curve, right? So this is the elastic curve. The tangent at B is this line, and tangent at A is this horizontal line. Since A is a fixed support, so there will be no rotation, and it will be our horizontal line. Now when you draw the angle from tangent A to tangent B, it is in the clockwise direction. And if you recall, we just mentioned that when the angle from tangent A to tangent B is measured in clockwise direction, it will be negative, right? Negative slope or rotation or angle. So coming to the solution, the M over EI diagram is presented in figure 3b. The force P causes the beam to deflect as shown in figure 3c. The tangent at B is indicated since we are required to find theta at B. Also, the tangent at support A is shown, which is this horizontal line. This tangent has a known zero slope for obvious reasons. By the construction, the angle between tangent A and tangent B is equivalent to theta B, right? Because theta B is also with the horizontal, and tangent A in this case is also horizontal line. So this theta B is equal to theta B by A. Therefore, theta B is equal to theta B by A. Now the first theorem indicates or states that theta B by A is equal to the area of the bending moment diagram. So in this case, the bending moment diagram is in triangular shape. So half into base into perpendicular will be its area. So you can see that half into base into perpendicular, and this is the value of theta B by A and theta B in this case. The negative sign indicates that the angle measured from the tangent at A to the tangent at B is clockwise. This checks since the beam slopes downwards at B. So this was a simple numerical. Now just consider this example, which says that determine the slope at point C on the steel beam. This is a steel beam whose length is 8 meter, right? The load or unit load is applied, sorry, not unit load, point load of 16 kilonewton is applied at 6 meter from A, 4 meter from C, and 2 meter from B. Take EST as 200 gigapascal. I is equal to 17 into 10 power 6 mm4. Now you know that for this we have to draw the bending moment diagram, and since EI is given, so you can just multiply them and divide this value by EI. But here we are presenting it in terms of 8 divided by EI and 24 by EI, right? This is our bending moment diagram, and this is the deformed shape of the beam. And as you can see from this statement, it says that at point C you need to find the slope, right? So this is the slope theta at A. This is our tangent at A. This is our tangent C, and this is our tangent B. Now at all the 3 points we have drawn the tangents, and the angle between tangent A and tangent C is called theta C by A. The angle between tangent C and the horizontal is tangent C, theta C, and the angle between horizontal and tangent A is this theta A, right? Why this is called the minus tangent C? Because you will understand it while we will solve this numerical. So step number 1 is to draw the bending moment diagram with M over EI. Done. Elastic curve. The elastic curve is shown in figure 4c, right? Here we are required to find theta C. This theta C is required. This tangents at the supports A and B are also shown. This is tangent at A and this is tangent at B. The slope at A, which is this theta A, the slope between tangent at A and the horizontal is theta A, can be found using this equation. Theta at A is equal to TB by A, which is this perpendicular distance or the vertical distance between the point B and the tangent A at point B, right? So theta A is equal to TB by A divided by LAB, A by LAB, which is the perpendicular over this base, right? So you can get this theta A very simply by using this perpendicular by base equation. This equation is valid since TB by A is actually very small, so that TB by A can be approximated by the length of a circular arc defined by a radius of LAB is equal to 8 meter and a sweep of theta A in radians. So if you remember this equation, S is equal to R theta, so this is very valid, right? From the geometry of figure 4c, we have theta C, this theta C is equal to this theta A minus this theta C by A, right? So this whole angle is theta A and this is theta C by A. So you can find this theta C by subtracting this theta C by A from this theta A, right? And this will be equal to theta A is TB by A divided by 8, which is the length of the beam, minus theta C by A, and this is our equation 1, which is for theta C in terms of theta C by A and tangent B by A. Now we need to find tangent B by A, right? Using first theorem for theta C by A, which is equivalent to the area under the MORE diagram between points A and C. So this is your point A and this is the point C. So it is a triangle with the base of 2 meter and a height of 8 over EI. So area is equal to half into base into perpendicular. So it's equal to 8 over EI kilonewton square meter. Now we found out the theta C by A, right? And we are left with tangent B by A. So applying second theorem for tangent B by A, and we know that it is equal to the moment of the area. So tangent B by A is equal to this is our tangent B by A, right? And it is equal to what? It is equal to the moment of the area. So 2 meter plus 1 by 3 of a 6 meter. This is our 2 meter, right? And this is 1/3 of the 6 meter, since its centroid or the resultant will act at 1/3 from this distance, right? Into this is the perpendicular distance or the moment arm, multiply by half into 6 into 24. So 24 is the magnitude, 6 is the base, and it is a triangle, and half is by formula, plus 2/3 of this 2, since this distance is 2 by 3. So 2 by 3 into this 2, right? And this is the moment arm, and into half into 2 into 24, which is the area of this triangle. Now on just solving this, we will get the value of TB by A equals to 320 kilonewton into meter cube or EI. Substituting the values or these results into equation 1, we will get theta C, right? Because we now got the value of TB by A and we got theta C by A. So just putting the values will give us theta C equals to 32 kilonewton meter square over EI. Using a consistent set of units, we have just putting the values of E and I, we will get the values in terms of radians, which is equal to 0.00941 radians. So this is the required answer, right? The angle it is showing is clockwise, therefore here it was mentioned minus, right? Now this is our last example of this lecture, and it says that determine the displacement at point C. This is the point C, and we have to find out displacement at this point subjected to a 5 kip of unit load. So these are the reactions: the 5 kip downward, 10 kip upward, and this is the bending moment diagram. That bending moment is negative, minus 60 over EI is the maximum bending moment, and this is the elastic curve or the deformed shape or the deflected shape. This is tangent at A, this is tangent at C, and this is the tangent at B, right? And this vertical distance is tangent B by A, and this vertical distance is tangent C by A, and this tangent C by A is equal to the mu C, right? Because this is the horizontal line or the original line, and the distance from this line to this deflected line or the point is called mu C, and this distance, the distance between the tangent A at point C, and this horizontal is called mu dash, right? So keep in mind that this mu C is equal to Tc by A minus mu dash. So we need to find this Tc by A and we need to find this mu dash. However, mu dash can be related to Tb by A over here, right? Because it can be solved by similar triangles. So once we can find this Tb by A, we can simply find out mu dash by similar triangles. So mu dash by 24 is equal to Tb by A divided by 12 from similar triangles. Therefore, mu dash is equal to 2 times Tb by A. Hence, mu C is equal to Tc by A minus 2 into Tb by A, right? And this is our equation 1. Now we need to find Tc by A and Tb by A, right? So applying moment area theorem, the second theorem says that these tangents can be found out by finding out the moment of the area, right? So Tc by A is the moment about point C of this whole diagram, right? So it will be equal to 12, which is the base of both the triangles, right? Of this triangle as well as this triangle. So 12 into half of 24, which is equal to the length of both the triangles, right? 12 plus 12 into 24. So half of the 24 into 60, which is the perpendicular, right? This perpendicular is the 60 into by solving this we will get this value of Tc by A. Similarly, Tb by A, which is equal to the single triangle. For example, the Tc by A is the area of both these triangles, right? And the resultant of this triangle was acting at a distance 12 feet from the sea, right? And the magnitude or its volume was half into 24 into 60. But Tb by A is the area of moment of area of this triangle, and its resultant will act at 1/3 from the B, right? So the moment arm will be 1/3 of 12. This is 1/3 of this 12, right? And the area of the triangle, which is half into base into perpendicular. So here we get 1440. Now it says that why are these terms negative? So substituting the results into equation 1, this is our equation 1, Tc by A minus 2 into Tb by A. So putting the C by A and B by A in this equation, so it gives us the value of 5760 kip into cubic feet over EI. As the deflection is downward, therefore the values were negative, right? Using a consistent set of units, putting the values of E and I, and we will get a value of 2.75 inch deflection in the beam at point C. So mu C is 2.75 inches at this point because of this 5 kips of point load applied at the free end of this 24 feet beam. And this was all about the moment area method. In the next video we will discuss about the method of superposition. So thank you very much, guys.